So the problem was given 5 numbers, x1, x2, x3 is 5 numbers, and they add up to 72. Now find xi, these x1, x2, x3, such that the product maximizes. Okay. So let us first discuss what happens if you allow xi to be negative. So xi's are integers. That let me say that xi they are integers. They belong in Z. And this is a very crucial thing. What happens? Because yeah, in the exam, if they don't say positive integers, they just say integers, then that's what it is. And then you have to see what the answer can be. What happens if xi, yeah, basically, if this is the situation, okay? If we allow xi to be negative. Right, can you give an example? You are right, but can you give an example? Yes, and you have to just make sure that you have an even number of negative numbers. Right, so yeah, by doing that, you can, so by taking, and Unab, I suppose you also see this, right? You can, right? Is that right? That if you take negative numbers, then your answer can be as big as you want. Right, because just to complete an example, you can take this and then you can take plus 10,000 and another plus 10,000, and then you can just take 72. This will be 72. So this is not a very good question, right? So because the product will be positive and then it will become as big as you want. So that is why this becomes an absurd question if it's just integers. But yeah, if it's just integers, then infinity is the answer. The maximum can be made as big as you want by taking even number. But this is also a point that you have to be, it's a logical issue that you have to be subtle, to be clear about. Logical. So it is wrong to say that you can make the maximum a very big number. Formally speaking, it is wrong, right? The correct way to say would be you can make it as big as you want, right? Like if one has to be precise, yeah, can be made as big as possible. So you can say that the maximum does not exist, or you can say it's infinite. Okay. Obviously, every time the product that you get will be a finite number only, but you can make it as big as you want. You can make it bigger than anything. So that's why. So this is not very interesting. Okay. And whenever products are given, usually you will see that we take the numbers to be positive. Okay, unless if there are squares and such, if it was squares, then it does not matter. Okay, so there you can take it to be negative also. But in our case, it's simple. So, so hence we adjust this question, or you can just write naturals. Now you guys can tell me your attempts. Sorry. Yeah, Unab, you can go first. But why do you take factors of 72? Yeah. X1 was a product. What does that mean? Try to frame it again. Say it clearly. Try to say it clearly. X1, see, X1 was a product doesn't mean anything. Just take a minute, try to frame it clearly and then say. I mean, you can say something which is wrong. That's obviously that's then obvious, but it should make sense. Right? Yeah. So just take a minute, think. Okay. So what do you think? So try to explain what you have done. Um, hmm, hmm. That's right. Okay. Okay. Right. So how should you choose the X size so that the product maximizes? So, I mean, why don't you try with smaller numbers? Did you try with smaller numbers? Uh, okay, okay, then just wait. Let's see. Okay, Ishana, what have you tried? Okay, 12 plus 24 plus 12 plus 12 plus 12. Okay, so that's also similar to what Una was maybe he was saying about factors, right? So, wait, is this 72? Yes, this is 72. Okay. So it's making sense, right. So if you say if you break up 72, if you subtract 36, then the rest of the numbers, if you divide them, then it divide them into four parts, and the answer reduces. So if we actually do that, it becomes 999, right? So then what do you get? You basically are saying that 12 to the power 4 times 24, this is bigger than, actually much bigger, but bigger than 9 to the power 4. Is what you're saying, right? Sorry. But here the power being bigger is, yeah, you are right in some sense. Yeah, that's right. Okay. But did you figure out if this is the best possible answer? 12 to the power 4 times 24. Is this the best? Okay. Okay. So what does the intuition tell? If sum of a few numbers is some fixed thing, how do you maximize their product? You can take us. So there are two ways, because see, first priority is that be able to answer this question, right, correctly. The proof you may not be able to do, that's a different thing, but at least you should, we should get the correct answer. So for that, there are two things that you guys should have done, and this is these two are easy. One is take small cases. Did anyone do this? What I mean by taking small cases is, instead of taking the number 7, you must understand clearly what I mean by small cases here, right? Instead of taking the number 72, you take some smaller number and then try. Just take the number 7 or maybe 10 if 7 is too small. Or maybe let me just not take 10, let me take 12, or let me take 13. Hmm. That's one. So let's try to find the, because we can find the exact answer in this case, right? And then you can see the features. So yeah, let's try this one. And then I'll tell you the other thing that you should have tried. Maximum number. No, so what I mean is maximum product. You have to choose numbers so that the product is maximum. Okay. Three fours, four threes. You said three. Yeah, you said the right thing. Yeah, I wrote the wrong thing. Three fours, sorry, four threes, and a one. So you can check it. I mean, this would give 3 to the power 4. Now you must ask yourself, can I make the product bigger than 3 to the power 4 by choosing appropriate excise? Just try different combinations now. I mean, maybe this is right, but you have to see. Can you increase the answer? That is the thing. Yeah, so can you modify some of the exercise? Can you modify some things here so that the answer increase, so that the product increases? Right? That is what we are looking for, right? I mean, try to maximize the product of the numbers. So this gives 3 to the power 4. Now the question is, can we modify this thing 3 plus 3 plus 3 plus 3 plus 1? When you modify this a little bit, tweak it a little bit so that the product increases, product of the new numbers. Okay, so you're also saying similar. Okay. What if you do, so let's say, what if you do 2, 2? Is this any good? Is this bigger? Right? This is bigger. Okay. So you see, you get a bigger answer. Yeah. So, sorry, this is 2 to the power 2. Now try to observe this problem for this case, or if possible, take another small example and see what is the nature of the choices you're making. It's not about the final answer, it's the way the numbers are chosen which maximize the product. Okay. So you can take another example and try. You can take any example, take 9 or anything. Or maybe a bigger example, you can take 15. Yes, right? 3 raised to 5. And this looks like it is the biggest, right? Again, we are not proving, we have not proved it, but it seems like that. Okay, now that we have done these examples, again, we have not given any reasons, but we're just going by intuition. So with this reasoning, I mean, you can understand what is happening. I'm not saying it because then that would be like giving the answer completely. What should be done in this case? The 72 numbers. Mhm. Just by the same. So what is the feature of these answers? Well, the feature is that we are trying to pick the numbers so that they are as close to each other, right? Whenever we are maximizing, right? That is something that we are seeing. Whenever we are maximizing the answer, we are trying to pick the numbers which are as close to each other. Okay. So try to apply this in the case of, so you've got the feature by taking the small cases. Now try to use it in this 72 case. So now we have a concrete philosophy. We have a concrete basis on which we are giving these answers, right? Pick the numbers as close to each other. You see, in these 3, this did not work because 3 and 1 were, I mean, this was not the best in that sense, right? Well, we can make it formal, but you understand this is better. The numbers are closer to each other. The gap is only 1, 3 and 2. So yeah, and this was the maximum. Okay, we have not proved it, but feels like that. We will prove it, but first we should be able to get the idea of what is the what is the formula and how to use it. Here we could make them equal in the case of 15, and we did make it equal, and this seems like it's the biggest. So just use that here. So give me, I mean, basically give me x1 to x5 so that they are as close to each other. Basically divide 72 into 5 equal parts, as equal as you can make them, keeping them natural. Otherwise, you can just if you can just say 72 by 5 if there was no constraint. But here we have some constraints, so that's why we are, it won't be totally equal. Fourteen. Mm-hmm. Okay, so you're saying 14, 14, 14, and then 8. You're saying this would be the breakup. But is this the, I mean, in this breakup, this is not the closest. The numbers are not as close. Yes, yes. Okay. This is not the breakup is not the closest. It doesn't follow the same philosophy. This has the same error as this answer here had, 3311. Same problem, right? So this will be pretty big, but it will not be the biggest. You can make it bigger. I mean, just try it out. If you make this 13 and make this 9, this product will get bigger. Okay, so so there is an obvious problem, right? 16. Yeah, so if you use 16, then it does add up. Yeah, but that my point was, but the point is this is also not, so this will be pretty big, but are these numbers as close as they can be? See, that's my question. Right. So 15 would be better, right? Yeah, I mean, if you're saying something, say it confidently, right? 15, right? 15 is closer because see, the philosophy is this thing clearly. Philosophy is put the numbers as close to each other. And here we have 16 and 14, and they are not as close to each other. So you were right. You were saying you can make it 15. So that's the point. You can make it 15, right? And it would increase. And that's simple. Let's just do that. So 15, 15. So yeah, so maybe this is better. Okay, is see, certainly by our philosophy, by our rule, this should be bigger, right? The lower one should be bigger because the numbers are closer to each other in in that sense, right? This 16 minus 14, this difference of 2 does not appear. So this should be bigger. And one can maybe also check it. So what does this amount to? So the claim is, let's first check it. If it's not true, then all of this is wrong, maybe. Let's check it. Then it's 14 into 16, 14. Wait, what is happening? 15 square. Yeah. So this becomes 14 into 16 is less than 15 square. And this is true, right? You can check it. This is 225. And how much is this? I don't know. Just check it. 16. Yeah, 224, just less by 1. Something like that, right? But it's less. So you see, so with this rule that you must pick the numbers as close to each other, yeah, you see, once you understand this rule clearly, then there will be no problem in deciding whether this will work or this will work. There should not be. Okay, because it's very clearly stated. Well, it's not formally stated because when I go to state it formally, then the means we might lose the idea. Okay, but so first let's understand it intuitively, right? Pick the numbers as close to each other. So this you may pick first is 14, 14, 14, 14, 60. You may pick first, but then you can try to see, okay, can I make this gap 1 instead of 2? And you can always do that, right? So this, but now the question is, why does this work? That is the thing. We understand the rule and now we need to prove. So that's a little, yeah, that's an interesting question. So let's just put this. So the maximum is 14 cube times 15 square. Okay, this is a maximum and the product. So maybe you can keep this like this. If the sum is constant, then the product maximizes when the numbers are equal. This equal I'm putting in quotes because you can't make it equal always. You can make it pseudo equal. Okay. So why is this true? Can anybody? So we have seen this empirically. Yeah. How? Mm. Mm. Okay, yeah. Mm-hmm. 15 into 16 is greater than 14 into 17 by 2. Oh, okay, so you can say that, right? Uh, okay, so you were saying this. Oh, sorry. The difference is 2. Okay, right. And the difference is 2. And you're saying that you can check this algebraically here. So let's check that. So first of all, you both of you know that the sum is equal. The sum is 2a plus 3 in both the cases. So let's check which one is bigger. Now you can do this in many ways, but let's just expand it first and see. Yeah, and it's very clear. Oh, the difference is always 2. So you were like completely spot on, right? Okay, that's very good. That's nice. Good. So you see, it's kind of now algebraically clear, but this is yet not a proof. Okay, but for two numbers, also when the sum is constant, you can see that if you break it up in this way, where the difference is equal as close as it can be, because 2a plus 3, you can't break it into two, you can't break it into two integers because it's a odd number, but a plus 1, a plus 2 is the biggest kind of, right? Because if you break it like this, then the number decreases. Like if you decrease the smaller number a to a plus 1, a plus 1 to a, and if you increase the bigger number, then the product decreases. And then you can further in the same way continue like this, right? I mean, you have to, formally speaking, you have to do this. You have to prove this, like you have to say this also, and so on, right? That the gap, I mean, as the gap increases between the numbers, the product decreases. Okay, so as the gap increases, the product decreases. When the sum is constant, is this fine with both of you? Both is fine, good, right? So this is the, yeah, this is the situation, and it is a completely fundamental thing, right? Because if you just think of the area of a square, that's what the other thing, right? If the perimeter is constant, if you are given a string of length, let's say 10, and you want to make a figure with maximum area, you would make a square, right? That's something that we all intuitively understand. You would make a square. So when the perimeter is, and I'm not writing that, when the perimeter is the same, you maximize the area by making it a square. Okay, and this kind of question occurs in hundreds of disguises it can be given, and in more sophisticated ways we'll see. But right, so now the question is, how do you prove this thing rigorously? This is not yet a rigorous proof because we have kind of only seen it for two numbers. So I'm just saying this, it's not a rigorous proof, but we understand the idea. Okay, so we have seen it for two numbers. Now how about a rigorous proof? How about proving it for, let's say, five numbers? How to prove for five numbers? So it's not very difficult. It's actually the way we did it for two numbers is what we are going to do. Okay, so let's try to see. This is a very combinatorial kind of inequality. The proof is not by, like, you can't just say AMGM inequality even if you know it, because this is about integers. Okay, so assume, and this is not a problem, assume that x1 is less than equal to x2 is less than equal to x3 and so on. Do both of you agree that this can be done? We can make this assumption, right? Because yeah, we can just make this assumption. This will help us to reason clearly. I mean, we don't have to consider the symmetries and permutations and so on. Okay, so suppose this is one particular thing, And let's suppose there is another solution, y1 less than y, because we have to compare two solutions, right? And we have to show which one is bigger, y5. Let's just comparing two solutions. Okay, let's say that both of them are solutions. Okay, which I mean is that okay, so here also the sum is 72, and I'm going to compare the products. Compare the products x1, x2, x3, x4, x5, and y1, y2, y3, y4, y5. Okay, we are going to compare these products. Sorry, just give me 1 second. One second now. Sorry, let me not compare two products. It doesn't really make sense. What I'm going to just take is, let's just take one particular solution. Okay, sorry, I just made a mess here. I had just pre-decided something. So if you take this particular solution where x1 is less than x2, okay, like this, then what I will say is that if, let's say for example, if x3 is strictly bigger than x4 is strictly bigger than x3. If x4 is strictly bigger than x3, okay, yeah, if x4 is strictly bigger than x3, then how can I improve this product? The claim is that I can improve this product. I can improve or increase the product. Well, you will see this is not completely correct, but you will see I can increase the product by taking any guesses. What will I take? What is the modification I'll make to increase the product? I will decrease x4 by 1 and I will increase x3 by 1. Right? So the bigger one I will, yeah, just to make more equal. And this is exactly what Ishana did for two numbers, right? For this is exactly the thing. The bigger one, so just to create less inequality, you just distribute the things equally. That's all. Okay, that's the way to create less inequality. Just distribute the things equally. I mean, in numbers in this case, right? And so we have to check, and this is very simple to check. And you see, it's just about the two, just the case for two basically. So yeah, I mean, the product may not increase, but it will not decrease. So you will see when you compare. So it's very simple to compare because you can cancel these things. So let me create some space and you can check. So now you see the question is so easy, right? You can understand. Basically, you can start from any solution, and as you make the numbers more and more equal, the product increases. Okay. So what we said is that when the numbers are as equal as they can, then the product is maximum. But that is part of a bigger truth that when you make the numbers closer, the product increases. And that's how usually the case is, right? If you see something which is true, a general truth which is true, like, uh, in the sense of like without those independent numbers, then it's usually part of a bigger truth, right? That's basically what's happening, right? And which is it's a dynamic thing. As you make the numbers more equal, it becomes bigger and so on. And then it becomes the biggest when the numbers are as equal as they can be. So this, and you can just compare this. This would just be x3 minus x3, x4 minus x3 plus 1, okay, which is obviously bigger than or equal to 0, right? Which is true, right? This is true because the gap, yeah. Oh, no, no, it's minus 1. Sorry, I mean, I meant to make the plus 1 on this side. Yeah, yeah. So this is the same as this, right? It is just, yeah, x4 minus x3 bigger than or equal to 1, right? So, yeah. So this basically means that if the gap is 1, then you really don't need to do anything, right? But if the gap is 2, so if x4 is bigger than x3, but not just is bigger than x3 plus 1, which means that the gap is 2, then your product strictly increases, right? So this means, so let me, so if you bring it here, so you first of all understand that if the gap between x4 and x3 was exactly 1, if that was the case, then the product does not increase. Then it doesn't decrease, doesn't increase. Right? And that's very, very obvious, right? Because if the gap is 1, the gap still remains 1, right? I mean, you decrease the bigger one and so on, right? Just uh, hold on. Yeah, right. It's okay, I suppose. Yeah. So then nothing really happens. But if the gap is more than 1, then the product increases, right? So that's the thing. So if the gap between any two xi, xj is more than 1, then product can be further increased. Is that right? Okay, so this means that eventually you must go to the place where the gap is not more than 1. Does everybody agree? Right? You, to find the maximum, you must go to the place where the gap is either 0, which is best, or 1. Not more than 1. Between any two numbers, the gap should not be more than 1. And that's what I mean by here equal. And it's clear because when you go to that place, that number, I mean, that product is bigger than all of the others because we have shown, right? Because it's gotten by increasing, because if you take some other solution where the gap is more than 1, you can increase it and increase. And finally, you reach to this one big thing where the gap is 1 or 0. And that is the maximum. So we kind of have proved it. Okay. So this idea of making this local changes to prove a global thing, seeing it for two variables and then kind of, okay. So you see, we are kind of starting with an arbitrary product and making these changes and doing an increase, making local changes and creating an increase to prove the result. That is the way we do it. This doesn't have any formula in that sense that apply this so and so inequality. Okay, but it's like studying the feature. So studying, so this is a situation with combinatorial inequalities. So maybe I can write that. This may not be very useful. Abstraction may not be very useful now, but point is that when you're looking at combinatorial inequalities, what do I mean by combinatorial inequality? It's a kind of inequality where you are not allowed to go beyond naturals. That's what makes it combinatorial. It's like a counting numbers is based on counting numbers only. When you have combinatorial inequalities, you first of all obviously get the idea. So combinatorial inequalities, there will be no algebraic formula usually. Okay, but you can get the idea of what gives optimum, what kind of solution gives optimum. Okay, and then you can prove it. And the way to prove it is to start with an arbitrary solution. Okay, start with arbitrary solution. It could be for this problem, it could be for maybe maximizing sum of squares, maximizing this, that, minimizing something, given product being fixed, minimize the sum. The same kind of questions can be asked, right? And the same thing will work, the same exact same idea, that you start with the first, you get the sense of what the answer should be for small cases, and then you prove it by start with an arbitrary answer which is legal in the sense that it is satisfies the constraints, the sum or the product, whatever is given, satisfies the constraints, get arbitrary answer and increase it by some simple operation. And that operation will usually be clear from the nature of the optimum. Okay? Simple operation. So basically that simple operation will take you closer to the optimum. The operation should be something that takes you closer to the optimum. Here, the operation I did of decreasing the bigger number is and increasing the smaller number is the natural thing to do, because it takes you closer to the answer where the numbers are equal, which we want to prove. Okay, so this is the recipe. There is no formula, but there is this recipe. Okay, so yeah. So just take a minute and see if you have any questions. You can just practice some other questions, like just take some other numbers and practice and see. But this is the, so no questions. So now you can just turn this question around and ask, fix a product and try to minimize the sum. Okay, so now x1, x2, x3, x4, x5, such that the product, and you can note this down and try this. Let's say now the product is, you can take anything, you can just take 100 maybe. Okay, product is 100. I don't know if this is, let's see, such that this and the sum is minimum. And maybe you can also do maximum. You can do both. Do for, so yeah, just you guys understand the question. Do for sum being max. You can write the question down and then do. You can frame the question down clearly. So do for sum being maximum also. So this is homework. You don't have to do this now. Note it down. Okay. All right. So try this. I mean, I don't know. This question, I suppose, can be very different because uh, product is a different game, maybe because factors and may not be available and so on. So you have to think. Do this small case. Yeah, this may be completely different in that sense. Okay, because factors, we don't know, very restrictive, right? There are so many ways to partition a number in using summations, but using product, it's very strange. Okay, it can be different. Prime number, then it just becomes very different. So think. But then also you should get a clear answer. Let's see. So today we're discussing these problems. So maybe we can